Okay, so talking about a really remarkable topic, and that is the acidity of alkynes. Right? Here's one thing you have not seen before. You have not seen a carbon with a hydrogen that gets ionized, right, as an acid. This should shock you, right? This is what I've this is an acid-base reaction where the atom is actually a carbon. So this is a big shocker. And so we're going to talk about now the acidity of alkynes. So remember now that terminal alkynes have a low pKa. Big deal, right? Look at that. This goes from 50 to 44, which is a factor of a million, right? Because this is a log scale, factor of a million. And then this then goes 19 units, okay, from an alkene to an alkyne. This terminal hydrogen right here is way, way more acidic than ethylene or ethene. Here's the reason why. I guess I just said this in the previous slide. Now I've got one more. Let me go to the reason why first. I forgot about that slide. So the reason why is that the hydrogen is bonded to, right, this, you can see there was, before this was deprotonated, there was another hydrogen here, right? It was bonded to a carbon that was sp hybridized. Well, that orbital for those electrons is an sp orbital, and it's much closer to the nucleus, right? So this is much more stable than this, which is more stable than this, okay? Let's go back a slide now, just to remind you that what we're talking about an acid-base reaction. The base comes here, strips off that hydrogen. These electrons go here, and we're left with a lone pair of electrons on a carbon, which is amazing. So, and we explain that with ARIO, which I just said a second ago, right? It's now the orbital that we're interested in to explain why that's so acidic. Okay, so what we have to do in order to strip that off is we've got to find some base that has a, let's see, the conjugate. We've got to find some acid that has a higher pKa than acetylene, right? And then consider the conjugate base of that acid. I know that's complicated, right? But let's take ammonia, for example. Ammonia's got a pKa of 38, right? And so if we strip off a proton off of that and make it amide, right? There we go, right there. You see what this is, the conjugate base of ammonia. Well, so sodium amide or sodamide, right, is a stronger base, right? So now this is the conjugate base of my favorite acid, water, right? And this has a pKa of 16. So since that's got a pKa of 16, its conjugate base is weaker than the conjugate base of acetylene, which is acetylide, right? All right, so again, you're setting up, you're just finding some, here's ammonia, right? Here's my favorite acid, water. And you can see that this is going to go in the direction of, this equilibrium is going to go in this direction. I know I've already complained about not feeling well today, but it's just difficult to push on, but we need these videos. All right, so let's, what are we doing here? What are we even doing? We've already said this, right? This is oftentimes done by sodamide, but other bases can be used as well. You figured out how, I sort of explained in a previous slide how you would figure out what kind of base could be used, right? This is the conjugate base of ammonia, right, which has a pKa of 38. So that's how you can evaluate things like that. All right, so you've got several pKa's that are memorized, and some of them are here. It's important to appreciate, right? Look at that. Tert-butanol. Here's tert-butoxide, right? Here's ethanol. Here's ethoxide. Here's ammonia. Here's amide. Hydrogen, hydride, right? And as the acid strength goes this way, right? This is a super weak acid. Here's a super weak acid. That would mean this would be a super strong base. Okay, So go memorize some more pKa's and practice what this means because it's going to give you lots of insight in terms of which way reactions are going to go. All right, good luck.